Okay, imagine a digital lockbox. Super, super secure. But here's the thing. It doesn't need some massive clunky key. It uses something. Well, something elegant.
Yeah, that's a great way to put it. And that elegance,
Yeah.
that's pretty much elliptic curve cryptography, or ECC.
Right, ECC.
Mm.
And in this deep dive, we really want to unpack what makes this tick, use some everyday comparisons maybe without drowning in the complex math.
Exactly. You mentioned wanting to understand the security aspect. Like, why is it so hard to crack compared to, say, older methods?
Yeah, precisely. Because you hear about it everywhere now. That little padlock in your browser.
Yeah.
HTTPS.
That's often ECC.
And Bitcoin, Ethereum.
Yep. ECC secures those too. Even things like iMessage.
Wow. Okay. So it's really fundamental. Let's get into it then. How does this elegant lockbox actually work?
Okay, so the starting point is public key cryptography. Basic idea. You have two keys.
Two keys, right?
One's public. Think of it like the mail slot on a public mailbox. Anyone can drop a letter in.
Okay. Easy enough.
The other one, that's your private key. Only you have the key to open that mailbox and read the letters.
Right. Makes sense. Public to lock, private to unlock.
Exactly. Data encrypted with that public key, it can only be decrypted using the matching private key, nobody else's.
Okay, I'm with you.
Yeah.
But what's the specific ECC trick here? What makes its process so secure?
The real magic is something called a one-way function, or sometimes a trapdoor function.
One-way trapdoor.
Yeah, it's a mathematical process that's like really easy to do in one direction,
Okay.
but incredibly hard, practically impossible to reverse unless you have a secret piece of info.
The private key.
That's the one. That's your trapdoor secret.
Oh.
In crypto terms, it's a deterministic function, easy one way, computationally infeasible the other way.
Okay, give me a real-world thing for that. Make it stick.
Think about mixing paint.
Yeah.
Super easy, right? Take some blue, add some yellow, boom, you get green.
Yeah.
But now, if I just give you the can of green paint, try separating that back into the exact original blue and yellow.
Yeah, no way. It's just green.
Exactly. ECC uses a mathematical version of that. Going one way, encrypting, is straightforward. Going backwards, decrypting without the private key is, well, it's like unmixing paint. Extremely tough.
Got it. Or like making a smoothie, maybe. Easy to blend the fruit together,
Right.
but try unblending it back into perfect strawberries and bananas. Forget it.
Perfect analogy. Now, you mentioned hearing about elliptic curves.
Yeah, where do they come in? It sounds kind of, geometric.
It is. The elliptic curve part literally comes from a specific kind of mathematical equation. It looks like it's x plus b.
Okay, that's the formula.
Yeah. And if you were to plot all the points, x, y, that satisfy that equation on a graph, you'd get this specific looping shape. It's got this neat symmetry across the horizontal axis.
So it's a visual thing, this curve. But how do points on the curve make things secure? Is it just the shape?
It's less about the overall shape itself and more about the mathematical relationships between specific points that happen to lie on this curve. That's where the cryptographic action happens.
Okay, so we've got this curve, we've got points on it. How do we use them for, like, locking our digital stuff? Is there some math we do at these points?
Precisely. And this is where it gets a bit weird, but cool. Imagine a bizarre game of billiards played on this curve.
Billiards, okay.
So you pick any 2 points on the curve, draw a straight line through them,
Right.
that line. It's guaranteed to hit the curve at exactly one other point somewhere else.
Always.
Always. Now, in our weird game, when the ball hits that third point, it doesn't just stop. It sort of bounces. Specifically, it reflects across the horizontal axis to land on another point, which is also on the curve.
Whoa, okay, so line through 2 points, find the third intersection, then flip it over the middle line.
You got it. And we call that whole operation, finding that reflected third point, the sum of the first 2 points. Or sometimes we just say we dotted them together.
Bizarre billiards indeed. And this dotting keeps you on the curve.
Always. That's the key. Whatever you do with this dot operation, the result is always another valid point right there on the curve. It's a closed system.
Okay, I think I'm tracking this weird billiard game. Combining 2 points gives you a new one on the curve. What if you want to do more? Like combine a point with itself.
Now you're getting to the core of it. That's called scalar multiplication.
Scalar multiplication, right.
Think of it like taking a whole bunch of shots in our billiard game, one after the other. You start with a point, say A, you dot it with itself, that gives you a new point. Then you dot that result with the original A again.
So you keep adding the original point to the result.
Exactly. If you want to multiply point A by, say, the number 5, you're basically doing A.A, then result.A, then new result.A, 5 times total.
Okay, so it's repeated addition, but using this weird dotting rule.
Precisely. It's like taking a specific number of steps along the curve, following our billiard rules. Now, it's really easy computationally to take, say, 1,000,000 steps or 1,000,000,000 steps and find out where you end up.
You keep dotting.
Yep. But, and this is the crucial security part, if someone only sees your starting point on the curve and your final point after all those steps, it's incredibly, incredibly hard for them to figure out exactly how many steps you took.
So that number of steps.
Yeah.
That's the secret.
That's the private key in ECC, the number of steps you took.
So going forward, taking the steps is easy. Scalar multiplication. But going backwards, seeing the start and end and figuring out the number of steps, that's super hard.
You absolutely nailed it. That is the one-way or trapdoor function for ECC. Easy to do, practically impossible to undo without knowing the number of steps. That's the security.
Okay, that makes sense. Now, ECC isn't the only game in town, right? I hear about RSA all the time. How's ECC different from RSA?
Right. RSA is definitely the older big name in public key crypto. It relies on a totally different mathematical puzzle.
It is.
The difficulty of factoring really, really large numbers, specifically finding the 2 prime numbers that were multiplied together to create a large composite number.
So multiplying 2 big primes. Easy.
Trivial for a computer.
But taking the result and finding the original primes.
Extremely hard, especially as those primes get gigantic. That's RSA's trapdoor.
Okay, so RSA is about hard-to-factor numbers. ECC is about hard-to-count billiard shots or steps. What's the practical difference for, like, you and me?
Well, one of the biggest practical advantages of ECC is key size. It gives you the same level of security as RSA, but with much, much smaller keys.
How much smaller?
We're talking like a 256-bit ECC key offering roughly the same security as a 3072-bit RSA key.
Wow, 256 versus over 3,000. That's a massive difference. Why does key size matter so much?
Several reasons. Smaller keys mean faster calculations. Encryption and decryption happen quicker.
Okay, speed. Nice.
Less computing power needed. That's huge for, smartphones, smartwatches, all those little Internet of Things devices that don't have powerful processors or big batteries.
Right, efficiency, energy saving.
Exactly. And less data needs to be sent back and forth when establishing a secure connection. Saves bandwidth. It just makes secure communication feasible for billions of these low-power devices.
Well, faster, less energy, less data. It sounds just better. Why was RSA used so much then? Still is sometimes.
Well, RSA came first. It had a big head start, got built into lots of systems, standards, libraries. Inertia is a powerful thing in tech.
Compatibility, maybe?
Yeah, compatibility, existing infrastructure. But there's a bit of a sustainability issue with RSA. As computers get faster, you need to keep making RSA keys bigger and bigger to maintain the same security level.
Because factoring gets easier with more power.
Right. And those bigger keys slow things down, especially on, well, those less powerful devices we just talked about. ECC scales better. The underlying math problem seems inherently harder, so the keys don't need to grow quite as drastically for the same security boost.
So RSA kind of risks getting bogged down by its own size over time, while ECC stays relatively lean and mean.
That's a good way to think about it. While the math for factoring does get better, the core problem behind ECC, we call it the elliptic curve discrete logarithm problem, the how many steps problem, hasn't seen the same kinds of algorithmic breakthroughs that make it significantly easier to solve for equivalent security levels. It just seems intrinsically harder.
Okay, let's dig into that a bit more. The elliptic curve, discrete. Logarithm problem, ECDLP. Sounds intimidating.
It does, yeah. But the concept is just what we discussed with the billiards.
The steps.
Exactly. Remember, you start with a known base point on the curve. You dot it with itself a secret number of times. That secret number is your private key, the scalar. You end up at a final point, which becomes your public key.
Start point, number of steps, private, endpoint, public. Got it.
The ECDLP is simply this. If I give you the starting point and the ending point, can you figure out the number of steps?
And the answer is basically no.
For practical purposes, with the key sizes we use, no. It's computationally infeasible, even for supercomputers.
So even knowing the start and end of the journey on this curvy path, you can't easily count the steps.
Not without trying basically all the possibilities, which would take, well, longer than the age of the universe for typical key sizes. Think of that complex maze again.
Right, the maze analogy.
You see the entrance, start point, and the exit, public key. But the path taken, the private key, the number of steps, is hidden within this incredibly complex structure defined by the curve and the dot operation. Finding that specific path without knowing it beforehand is just astronomically difficult.
Okay, that really clicks. How does that compare to breaking RSA again? You said factoring is getting better.
Relatively speaking, yes. Mathematicians have found clever algorithms like the general number field sieve that get more efficient at factoring as the numbers get bigger, relatively speaking. Still hard, but there are known pathways.
But for ECDLP, not so much.
Not in the same way. There aren't currently known algorithms that offer a similar significant shortcut to finding that secret number of steps for ECC compared to the best methods for factoring for RSA. The structure of the problem seems more resistant.
Okay. What about the elephant in the room, quantum computers? Aren't they supposed to break all this crypto stuff?
That's a huge area of research. And yes, RSA is considered very vulnerable. A powerful enough quantum computer running Shor's algorithm could theoretically factor those large numbers relatively easily, completely breaking RSA.
Game over for RSA, potentially? What about ECC?
ECC is currently thought to be more resilient. There is a quantum algorithm, Grover's algorithm, that could speed up the search for the private key, effectively reducing the security level.
So not immune, but better.
It would likely require a significantly larger or more stable quantum computer to break ECC compared to what's needed for RSA. But yeah, not totally immune. That's why researchers are actively working on post-quantum cryptography, new methods resistant to both classical and quantum attacks.
Okay, so ECC looks stronger against current and near-future threats, including quantum ones compared to RSA. That must build confidence. Does that translate into real-world use? Where do we see ECC deployed?
No, absolutely. It's widespread. Governments use it for securing sensitive communications.
Makes sense.
The Tor network, for anonymity, relies heavily on ECC. We mentioned Bitcoin ownership verification.
Right, crypto.
Apple's iMessage end-to-end encryption. Protecting DNS queries with DNS over HTTPS. And, of course, securing trillions of web connections daily via TLS SSL, the thing that gives you HTTPS.
It really is almost invisible plumbing for digital security.
It is, and companies like Cloudflare, who handle a massive chunk of internet traffic, use ECC extensively, especially for something called perfect forward secrecy.
Perfect forward secrecy.
Yeah, it's a crucial feature. It means that even if someone somehow compromises a long-term private key in the future, they still can't go back and decrypt past conversations that were protected by temporary keys derived using ECC. It protects your past messages even if a future breach happens.
That's incredibly important for privacy.
Hugely important. And you hear experts expressing concern that the math behind RSA and similar older systems like Diffie-Hellman might realistically be breakable within, the next decade or so. ECC is widely seen as the more robust successor already in place.
So it's not just niche. It's becoming, or maybe already is, the workhorse for serious digital security, based on that really tough math problem that's hard to reverse.
That's it, exactly. It's that secure digital lockbox. But the key mechanism, while small and efficient, is just incredibly difficult to pick.
Okay, let's try and wrap this up. So ECC gives us strong security, but with smaller keys and faster performance than older methods like RSA.
Check.
And it achieves this using the mathematics of elliptic curves, specifically the difficulty of that how many steps problem, the elliptic curve, discrete logarithm problem.
You got it. Easy to go forward, incredibly hard to reverse.
Which makes it more efficient, better for mobile devices, and seemingly more resilient against future threats, including quantum computers, at least for now.
That's a perfect summary. It provides a really solid, efficient foundation for securing our increasingly digital lives.
This has been fascinating, really demystifying something that sounds so complex. It's amazing how this elegant math underpins so much. It definitely leaves you thinking, as our world gets even more digital, even more connected. What comes next? How will math and computing keep evolving? Could there be something beyond ECC waiting in the wings? Maybe an even more elegant, even more powerful way to secure everything. Definitely food for thought.